We have here triangle ABC. And what we're going to do is we're going to look at how sine can be used on triangle ABC even if triangle ABC is not a right triangle. It's important to clarify a couple of conventions here. In geometry, by convention, we're using capital letters to represent points. And also, it is convention to use lowercase letters to represent side lengths. Also, notice that we're using the letter A to represent the side length that is opposite of angle A. Capital letter representing the point, the lowercase letter representing the side. We could also represent this side as BC. If we write it like that, we mean the length BC. If we write the segment symbol over the top, we mean segment BC. It's also worth noting that we often use Greek letters to represent angle measurements. So a secondary convention in a triangle like this is to use the first three letters of the Greek alphabet instead of the first three letters of the English alphabet to represent the angles. And in that context, we would call angle A angle alpha. Angle B would be angle beta. And the third letter in the Greek alphabet is gamma. And so angle C would be gamma. And so it's just be useful to use a convention that works for you, but also be comfortable recognizing these different conventions and understanding the way that they're used. So we're going to try and recognize a way that sine can be used to discuss this triangle. And the first thing we're going to do is we're going to talk about what sine of A is. Up until this point, sine is defined as the ratio of sides in a right triangle. So we need a right triangle. And what we're going to do to create one is we're going to draw the altitude of triangle ABC from angle B to its base. And we'll label this H. And we're going to then at the bottom, we've got side length B split up. But since we're working with sine, we're going to find that we don't really need to represent either of those because sine of A is now the opposite side length divided by the hypotenuse. Sine of C is equal to the opposite leg divided by the hypotenuse. Keep in mind, H here stands for the height, not hypotenuse. And we can isolate the H in both of these equations. So we could turn this into H is equal to C times sine of A. And the second equation we can turn into H equals A times sine of C. And in both of these equations, H is going to be the same length because they both represent the height of this triangle. So we now know that C times sine of A will be equal to A times sine of C. And now as long as you have three of those pieces of information, you can solve for the fourth, even though this isn't a right triangle, allowing you to use sine to talk meaningfully about them. This is not typically the form that the rule is written in, so let's just manipulate it slightly to get it into the correct form. Typically, everyone would divide both sides of this equation by A and divide both sides of the equation by C. And so if you look up the law of sines, you're going to see it in the form sine of A over side length A. Again, that's the side length across from angle A, is going to be equal to sine of C divided by the side length that's across from angle C. And then even though we didn't set up our triangle to represent the ratio sine B and B, it's also true that sine of angle B divided by the side length of that is opposite of B will be equal to these. And so we get this relationship of ratios, sine of an angle divided by the side length opposite it. Those ratios will always be equal in any triangle. And we can then use sine on triangles that are not right triangles.